So we looked at the problem in the bounded domain. What we take up next is the unbounded domain. Okay. So we see what happens in the case of unbounded domain. So let me just D becoming the whole of R2 or a part of it or some infinite strip of it or any such thing. Now then you have the following corollary. If D is unbounded, under the conditions of the theorem, that means the function is continuous in the domain and the function is locally Lipschitz. As x tends to x0 plus m, that is the extent to which the solution is defined, either there are two possibilities. Yx become unbounded. As we have seen in the case of that y derivative is equal to y square, we have seen as x tends to x0 plus 1 by y0, that is your x0 plus m, the solution becomes unbounded. Okay? Or the second possibility is that yx actually approaches boundary. So these are the two possibilities. So here we are assuming the condition that you assume is that f is continuous and f is locally Lipschitz. An example, a typical region of this type is the whole of R2 or some strip like this, or even a region something probably takes the form something like this. It may not be bounded at all. In some part there is a well-defined boundary, otherwise it is unbounded. All these kind of domains may come. So in which case what happens? Suppose you take this. So you start with an x0, y0. Then what you say is that the integral curve, now you see, here it approaches boundary, the infinity, or it may tend to a finite limit. or here, see, this is the interval on which it is defined. So it is defined from say x0 to infinity. As we have seen in the case of that fxy is equal to y square, we have seen the interval. Each solution has an interval on which it is defined. It is defined from, some solutions are defined from minus infinity to a point, a definite point on a finite value for x, or in an interval of the type some y to infinity, depending on the value y0 is positive or y0 is negative. So all these situations can arise. Okay. Therefore, let us, the proof of this is just 2 lines. So we have a possibility that y becomes unbounded. If option E, that is possible. If not, if it is not true, if the solution is unbounded, is bounded, or what you call is not unbounded, then we can replace the domain by a suitable domain. Suitable bounded domain. And then the previous theorem applies. So there are two possibilities: either this function becomes unbounded, in which the case A, or we can replace it by a bounded domain, and once the bounded domain comes into the picture, so this problem, this approaches the boundary, xyx approaches the boundary as x tends to x0 plus m. Okay, so that's the that is the result. So that tells everything about the behavior of the solution. The solution can be extended from the point from x0 minus h to x0 plus h until it approaches the boundary or it becomes unbounded. We have seen that example, y dash equal to y square, in which both these things are happening. On one side it becomes, it is defined on the interval minus infinity to, that means it need not be a finite interval also. On the other side you see that it goes up to x0 plus 1 by m, 1 plus y0, x0 plus y0 is the limit that you have. And you see that when y0 is positive, this is greater than x0. So, and as x tends to x0 plus 1 by y0, the function becomes unbounded. Yx becomes unbounded. That's the case. Now the next theorem gives some more insight into certain class of special cases. That's very interesting. We consider the type of problems which are defined on infinite strips. What we prove is the following. Suppose the domain is something like this. Suppose the domain is something like this. So this is x1, this is x2, and this is the infinite strip that you are looking at, and this is the domain. Okay, and the second condition is the following. We assume, so this is D, so D is taken as this is the interval cross minus infinity to plus infinity. So this is the region in which the problem is given, that is f is given. Now we assume the following. The assumptions that you make are f satisfies Lipschitz condition, f is continuous, on T, f is uniformly Lipschitz on D, that is the second condition. Then the integral curve passing through or I will just put it, say, and then make a statement of the theorem more precise. Then all integral curves are defined on the interval x1 to x2. That means that every solution of this problem has its graph something like this. Everything is defined on the whole interval x1 to x2. So look at the problem. It is the domain D is an infinite strip on which we are making two assumptions. One, of course, the usual assumption, it is continuous. The second assumption is that f is uniformly Lipschitz on D. What does it mean? This means f x y say is less than or equal to where m is finite The important point is that, see, in general what you get would be m which is a function of x. Okay. Or even a function of x and some y. So this may vary or what you call locally Lipschitz. We are assuming now it is globally Lipschitz in the sense that in this entire region there is one constant m such that this is true for every choice of x, y, x, y tilde in belonging to D. Once this condition is satisfied, then it is the every solution is defined on the whole interval x1 to x2. This is a very useful information that you have. For example, you look at this problem, y dash is equal to y. Or, okay, then what you have f of x y is, or even y x square. Now you take the d. Now what about f of x y? Therefore, f of x y1 minus f of y2 is less than or equal to And you see that you take x as the maximum of value of x1 and x2. So this number, you can find a number m, and what is the maximum value that you can take? So it is, you can accept this as x equal to, or m equal to x2 square. Okay. Once you fix x1 and x2, this is the case. So it is uniformly Lipschitz. Whereas you looked at this problem, this is not uniformly Lipschitz. In any region, okay. So this is a very nice piece of information, that where the solution exists. The solution for such problems where the f is uniformly Lipschitz, you see that the solution is defined on the entire interval x1 to x2. Well, let us give a quick proof of this. Okay, let me state the theorem. Be continuous in the strip you can take x closed interval x1 to x2 and assume that f is uniformly y the integral curve passing through is defined on every solution is defined on the interval x1 to x2. So again, see, in all these proofs, typically what you do is you assume the contrary and then get a sort of conclusion. So the problem is well understood, I suppose. You have an infinite strip. This is D, which we assume f is continuous and is uniformly Lipschitz in Y. Now we This is x1, this is x2. Now you see that looking at the problem and the function, the moment you see that on some infinite strip it is uniformly Lipschitz, then yes, then it immediately follows that there is a unique solution of the problem on the interval x1 to x2. So we start with the assumption. Suppose there exists an x tilde such that x0 less than x tilde less than x2, beyond which that means you have some x tilde. The solution is defined. Suppose x0 is this point. It's defined only on this interval, and beyond that it doesn't go beyond that. This is your x tilde. Then we show that yx is bounded that means if you take a neighborhood of that, then you get a bounded y the corresponding to that. Suppose you call this point some x1, this point as some x hat, something like that. Then at x hat y x hat is is bounded, or y x hat is bounded. So we will prove that. So what we do is we take one approximate solution. So consider yx solution of suppose you take this as a approximate solution of y dash. Any function you can take, because what you estimate is this. Then what happens? Apply the fundamental inequality. I put y tilde here. Y tilde x is defined as y0. That means, see, you are taking the point x0, y0. This is x0, y0, and this, the graph given by this is y equal to y0, which you call the which you call a solution y tilde. So y tilde x is taken as the constant function. Now apply the fundamental inequality for this. So what do you get? You get dy tilde by dx minus, it's a smooth function, differentiable, and what you have is minus f of x y tilde. This one is what? This is equal to d of a constant, because y tilde is taken as y naught, therefore dy tilde by dx is equal to 0. So this is equal to 0 minus so you see that what is the maximum value? So fx y naught, and you see that the supremum taken over the interval x naught to x naught to x tilde. Okay, and this you know is, this is finite. This is finite because it is the value of the function at see the value of the function for x y naught. So some point on this, it is finite, is finite. It depends on x, and you can, if you take on this interval, this is a compact interval, and therefore you have this finite. Now therefore we can work out the error. Or we can use this to show that the function yx is bounded. See this, the finiteness of this comes from the fact that f is a continuous function of x, because y naught is fixed. fxy y naught is a continuous function of x defined on the compact interval, therefore it is finite. So let this one x tilde denoted by m. Now you apply the fundamental theorem. So what will be the difference between the solution yx minus, let us estimate this, y tilde x is y naught, therefore this is equal to yx minus y naught. And this is because both yx and y tilde and y tilde x satisfy the same initial condition. Therefore, the first term in the inequality is 0. Therefore, the bound is given by m by k, that is the error. This is your epsilon turns out to be this particular m. So m by k e to the power k is the Lipschitz constant for x naught this is the bound that you get. Therefore, what you have on any such interval, the function y is bounded. In every neighborhood of x equal to x tilde. In every neighborhood of this, the function yx is bounded. So that much information we have. We may not know what exactly the y is, but certainly we know that it's a bounded function. Okay. Therefore, which implies, see, it is defined, we are assuming it is defined only on the intervals x naught to x tilde. As x tends to x tilde, the function y or the solution y of x of the initial value problem is bounded. Okay. Therefore, by applying the first result, what do you get? Or by the previous corollary, if it is bounded, then it approaches the boundary. That's a contradiction. Why? Because if you start with the solution, then this solution is bounded, and you know that you are assuming that it is defined only up to x tilde, and you see that since it's a bounded solution, it should approach the boundary, but the boundary on this side is this strip, because of the special nature of the strip of the region. You see that it cannot approach x2, which is a contradiction. Okay, right? Therefore, but this is impossible. Possible, because we are assuming x2. Okay. So that is a contradiction. So this does not comply with the theorem that we have proved. So it is beyond x tilde up to x2. Okay. So that's how we get the contradiction. Therefore, what you observe is that if you have your domain as an infinite strip and on which the function is uniformly Lipschitz apart from the continuity restriction, then the solution of the initial value problem should be defined on the entire interval. So that has lot of consequences. The consequences are that, suppose you look at this equation. Suppose this is defined R2. And we also assume for every strip see, this constant might differ, but on every such strip the function is assumed to be Lipschitz with respect to y. Then what you can say is that the corresponding solution of the initial value problem is defined on the interval minus x1 to x2. Now since it is true for every such strip, since it is true for every strip x1, x2 cross minus infinity plus infinity, it follows that the solution is defined then defined for the entire interval minus infinity to plus infinity. Okay, so that is one of the conclusions that you can make. Let us look at a specific problem. Okay, let me take up the specific problem. To take f of xy where p and q are polynomials. So what do you get? You see, you immediately infer that the function f of xy is continuous on for every choice of x2. That is very easy to see because these are polynomials. This is cos y and sin y functions. Now you can work out the the derivative of this. df by dy equal to, what is it, minus px plus 1. Look at the bound for this. Mod sin y is 1. So on every interval, this is bounded. Bound for px and bound for qx. Say on this interval you can suppose m1 is the bound for this and m2 is the bound for this, then you know that the polynomials are bounded on these compact intervals. So we are making use of that. Less than or equal to some m. So it is uniformly Lipschitz, and that turns out to be the Lipschitz constant. So it is uniformly Lipschitz, therefore you can apply this theorem and conclude that the equation y derivative equal to see, if you take this equation, where p and q are polynomials, as the integral curve, as the solution defined on. So you see a wide class of equations do come under this road. So even without solving, see, it is impossible, I mean nearly impossible to solve this exactly. Okay, all these equations, the results that we are proving are statements concerning the general equation where you may not be able to find the solution in the explicit form. Okay, in that case what you are concluding now is that in this case, in this particular case, you see that the solution, every solution is defined on minus infinity to plus infinity. Later you will see in many places we will be applying this particular result. It's a very good general result that you have to see how, on what interval the solution will be defined. Now what one can do is give some error estimates. Okay, I will state the theorem. Now you see that the advantage of the Cauchy-Euler method of approximation is this. How did we work on that? You have some interval on which you are constructing the Cauchy-Euler approximation. There is a geometric way in which you construct the function, which is what you call piecewise differentiable, and defined on each interval. It is continuous but piecewise differentiable, not necessarily differentiable on the whole interval. Such a construction can always be undertaken on any interval under the conditions of that theorem. If so, what is the that you can do? You can keep the error in the choice of this approximate solution to the actual solution of the initial value problem, to the level within the error that you stipulated. That is, once epsilon is given, you will have to choose the number of subdivisions that you have to make for the interval. It's like this. See, you have to say suppose you have an x1. Now you are making an approximation on this approximate solution. Then what do? You first fix the error. Once you fix the error as some number epsilon positive, you have to subdivide this interval and then make a sort of solution like this, something like this on this interval, and you can do that in such a way that the error between the approximate solution that you make and the actual solution of the problem, say the solution may be something like this, is restricted within this epsilon. This is obtained if you choose a smaller epsilon, then you are choosing the interval length sufficiently close. Okay, but you can always do it. That's what we have proved in the beginning. Okay, this is against, I mean, when we do the what is called Picard's approximation, we will see the difference between the two type of solutions. Okay, so that is the advantage. So let us see or make this sufficiently clear. So let us consider the theorem. Let x naught y naught and define some x equal to x1. Then what we prove is this: using Cauchy-Euler method, yx1 may be determined to any degree of accuracy by a sufficiently find subdivision of that means you can approximate the solution as closely as you want on the interval x0 to x1. What you need is increase the number of subdivisions. Okay, this is quite simple to prove, and I leave it you to work out the proof. You know, looking at the way in which you work the theorem. Okay. So with these remarks, now what have we done? We have shown how far you can extend the solution. Secondly, what happens to the solution at the extreme endpoints? The situations are either xyx approaches the boundary, or the y becomes unbounded as x tends to x0 plus m. This is, and likewise at x0 minus L also. And also we have seen that if you are considering a strip, and in that infinite strip the function is uniformly Lipschitz, then the solution is defined on the entire interval x1 to x2. Okay, and finally it says that the solution can be approximated as closely as you want using the Cauchy-Euler method. Only thing is that the refinement of the interval will have to be increased if you want to get greater accuracy. Okay, but what is happening is that you are talking about the error kept within a certain limit. I mean, this means the following. Geometrically, this is what it means. Suppose this is the point x0 by 0. Suppose this is the solution, this is the integral curve of the solution. Actually, we don't know what it is. We are not able to find it out. That's the problem. That's why you go for approximation. Now, what is this? You want another function which approximately satisfies this equation. Okay. So, what you are estimating is, suppose yx is the actual solution, then you are finding out the approximating function, and the distance between them we want to keep this less than epsilon on some interval. Okay, that means you are, see, this is xyx. You are defining a strip surrounding this one of width epsilon. The error that you allow is, or you allow the function y tilde x, the graph of the function y tilde x, to lie in this particular strip. Okay, so this strip would consist of points which vary from the curve y equal to, yx, this particular curve y equal to yx with an error of epsilon, or in other words, what you are saying is that y tilde x So that the graph actually lies somewhere here. So you are seeking a function which may be something like this, which lie in this particular region. This can be done. That is the content of this theorem. Okay. Once you fix your epsilon, what you possibly need is the function to be not differentiable at far many number of points. Okay. So the accuracy will depend on that. Okay. Thank you very much. I think next lecture we will take up what is called the Picard's approximation. Now please look into the book by Horowitz for the details of the proof. Thank you very much. Hello. Is there anyone there? Om, are you there? So how is it's okay? Yeah? I don't get you. Will you please look into the details of the proof from the book? Do you have a copy of the book?
Yes, sir. PDF.
You have a PDF copy, yes. Then you can actually look into the proof and then try to understand them, because at least read that once and understand it once. Because what is important is that how to work out proofs of results using techniques in analysis. Okay, so this is a good experience in doing that. Okay.
Yes, sir. Very good.
Okay, sir.
Okay, thank you very much. So I will be doing what is called Picard's approximation and probably the fixed point theorem in the next lecture.
Okay.
Yeah. Okay, Shruti, can you send your biodata to me in WhatsApp?
Yes, sir. Sure. I will send.
Yeah,
Yeah. Okay.
please. Okay, so I am signing off now, right?